Alrighty, welcome back to topic 11.8. This is our RC circuits daily video where now we're going to look at our non-steady state conditions for our open and closed switch scenarios. My name is Dr. Kelly Miza. I'm from Delaware Valley Regional High School in Frenchtown, New Jersey. Let's review. Alrighty, so the last couple of times we've met in these lovely videos, we have talked about an RC circuit where we have the voltage charge across a charging capacitor, the voltage and current through a resistor when our capacitor is charging, the voltage and charge across a discharging capacitor, and then the voltage and current through the resistor when we're discharging our capacitor. So as a reminder, they either have this nice 1 minus e to the negative t over RC dependence, or the straight up e to the negative t over RC dependence. So let's actually look at what that looks like. So you'll notice that in the exponent of our exponentials, that negative t over RC. RC is what we call the time constant. And the time constant of an RC circuit is a measure of how quickly the capacitor is going to charge or discharge. And we use this little tau symbol sometimes in order to represent our RC time circuit. And then if you have more than one resistor or capacitor, your RC circuit, your RC time constant is just the equivalent resistance times the equivalent capacitance. Okay, so when we're charging the capacitor, if we make some nice little graphs of charge versus time, that charge equation looked like 1 minus e to the negative t over RC. Anytime you have that 1 minus e dependency, that means you are going to be growing and you're going to have some asymptotic behavior up until your maximum charge. So what the RC time constant tells you, if we actually plot a nice little vertical line at t equals RC, that intersects our charge graph at about 63% of your max charge. So sometimes you're going to get questions that are like, well, after like how much time do you get to 63% of your maximum charge? And you need to be like 63%, beep, boop, bop, boop, boop. That means time constant. So your time constant tells you when you get to 63% of your max charge. All right, we've closed our switch. We're charging this up. That's what our charge graph looks like. When we're discharging our capacitor, on the other hand, we've now closed it this way. Boink. So we're already full, and now we're rapidly decaying. We have that e to the negative t over RC dependence. So we're losing that charge at an exponential rate, if you will. If we put that back into our t equals RC, that time, instead of gaining 63% of our charge, we've lost 63% of our charge, which means we have 37% of our max charge left. If you remember 63%, that's the one to remember. But how do I know what equation to use, Dr. Miza? Is it e to the negative t over RC or 1 minus e to the negative t over RC? Think about it. Are you growing to an asymptote or are you decaying to zero? If you're decaying to zero, it's going to be the explicit, just the decay. If you're approaching some maximum, it's going to be the 1 minus. So let's look at an example. Alrighty, Rue. I have, boom, this lovely capacitor right here. It's uncharged. Our battery is 10 volts. We have a resistance of 100 ohms and a capacitance of 10 microfarads. And I'm going to flip my switch, boom, to switch 1. So we're going to charge it. And we're going to plot these lovely charges. So I'm going to plot my voltage across the capacitor versus time. So my voltage, if I'm charging, it's approaching a maximum value because it's going to eventually have the voltage of the battery, right? So if I put my function here, because we're in Desmos, we have to be a little creative with our variables, but it's going to be my maximum voltage, 1 minus e to the negative t over RC. It's x here because it's the x-axis. All right. So I'm going to set my voltage to 10, my resistance to 100, and my capacitance to 10 microfarads. I'm going to make a nice little horizontal line at my maximum voltage V. That's my purple dotted line, boop, 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 that nice little asymptote right there. And I'm going to make a vertical line at T equals RC, boop, 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 to show my time constant. So if I come and see where does that intersect my voltage graph? Well, that intersects at time, R times C. And oh, look, 6.321 volts, which is 63% of our max voltage of 10 volts. Yes. Our voltage rapidly starts growing after 0.001 seconds or 1 millisecond. We're 63% full. And then we're going to keep growing until eventually we taper off and we're like, all right, I'm done. I'm full. Have fun. So now we're charged. Let's see what this looks like when we're discharging. So I'm going to flip my switch to position 2. So now my capacitor is full. It has a voltage of 10. And now I've switched it over and now it's discharging through that resistor. So it's like, woo, decaying down to 0. It's going to empty. If I make my lovely little Vmax horizontal line and my RC time constant vertical line, I can see where those intersect again. And at that time, 1 millisecond, or my RC value, I have 3.679 volts left, or about 37% of my max voltage, which means I lost 63% of my max voltage. So 63%, that's the number to remember. Okay, so let's practice. Let's do an example where we have more than one resistor and more than one capacitor. So here we go. We have 2 resistors in parallel, which means we can find their equivalent resistance. Yay, resistors in parallel, that's the reciprocal relationship. So I got 1 over R plus 1 over R equals 2 over R. And if I take the reciprocal of both sides, the equivalent resistance of those 2 resistors is R over 2. I also have 2 capacitors in series, which is our reciprocal relationship. Remember, those are opposites, resistors and capacitors, which fun, great. All right, so we got 1 over C plus 1 over C for 2 over C. So our equivalent capacitance is C over 2. Okay, well, that means our circuit behaves the same way as if I had just 1 resistor with R over 2 resistance and 1 capacitor with C over 2 capacitance. Well, now we can treat it just like a regular RC circuit, which means its time constant, tau, is R equivalent times C equivalent. That's just R over 2 times C over 2 for a total RC over 4. So if I want to answer a question that's something like, when will the capacitors reach 63% of their max charge? Remember that 63%, that's our key number that relates to our time constant. So we reach 63% of our maximum charge at T equals time constant. So our time constant in this case is RC over 4. So that is also the time I'm going to reach 63% of my max charge. And if I'm discharging, I'm losing 63% of my max charge in that time RC over 4. So when I'm discharging, I'm going to reach 37% of my max charge when I've lost 63% at RC over 4. So what should we take away from this? So the big one that always trips students up is, am I using the 1 minus e to the negative t over RC, or am I using the e to the negative t over RC? Just think about it. Like, if you were a charge in this circuit, what would you do? Would you be like, yay, capacitor, let me go over there? Or would you be like, no, capacitor, let me leave? If your capacitor is emptying, you're losing charges, things are shrinking, you're going to have that decay behavior, that e to the negative t over RC. And then with like your max charge, voltage, current, whatever it is that you're looking at in front, if you're growing and approaching an asymptote of your max charge or your max voltage, that's going to be this 1 minus e to the negative t over RC. And you can also think about, if t is 0 or t is infinity, what do these equations tell me? Well, if t is 0, this gives me 1. So that means I'm starting at my maximum and I'm rapidly decaying, because if t is infinity, this goes to 0. Whereas over here, if t is 0, this is 1. So I'm starting at 0, I'm starting at nothing, and I'm growing as the second term goes to 0. Thanks, and that's it.